Hello and welcome to the second video in my video series about creating games. Now, in this series, we're going to be talking about how to create a little Pong clone. Pong is a very nice, simple starter game because it provides you with two paddles, one that you control and one that is controlled by a computer, scoring, and has a win condition where you are trying to score a certain number of points. In our case, we're going to design a game where whoever scores 7 points first is the winner. It's going to be a pretty simple game, but you'd be surprised at what kind of challenges come up during game development. In the previous video, we installed the Pixel Game Engine and got it to run. I'll be doing it on my Linux computer, but you should be able to follow along just fine even if you are on Windows. As I mentioned in the previous video, you just have to run them in a different way. So this was the example we ran last time. It just displayed a bunch of pixels on the screen. And we're going to be talking about how to display the proper graphics today and manipulating things. Looking at the program, C++ initializes things through a Pixel Game Engine class, as we call it. We're not going to dive too much into what classes are today, but it is important to know that the Pixel Engine game class is created. When the engine is created, there are two important functions it makes, which we do all of our game code in. One is what's called the onUserCreate method. This happens the moment the engine is initialized and preparing to start running the game. If you had, say, images or sounds to load, onUserCreate would be a good place to load all of them, or maybe you have to set up some variables ahead of time. We'll actually be doing that today. Then there's a second function here. It's called onUserUpdate. onUserUpdate is a loop, or it's in a loop essentially. Most game engines have this update loop where you put all of your game logic in. And some game engines even have a draw loop, which is separate from the update loop. So typically when a game engine starts, first calls the create method. And then after that's all set up, then it runs an update loop. And since this is in a loop, this will go on forever and ever and ever. And until the update loop is canceled, then the program ends. It's a pretty simple loop. Some game engines will have in a separate thread a draw loop. And all a thread is a separate process. So while the update loop is constantly doing its thing, the draw loop is also doing its thing constantly. And some game engines do this so that all of your drawing code and all of your updating code is kept separated from each other. It's just a way to visualize it. It's actually how I like to do my programs as well. So we're going to be doing that today. Now, the Pixel Game Engine has a lot of drawing functions. As you saw already, there was a command to draw a bunch of random pixels on the screen. I'm going to go ahead and get rid of that now. Both of these functions have a boolean, as we call it, that it needs to be returned either true or false. If at any point you return false on the onUserUpdate or onUserCreate functions, the game simply ends. So if I were to run this right now, the game would just end immediately because we are saying return false, so that ends the game. This is just a way to tell the engine, hey, I'm done with the game. So let's talk about drawing things. I have this handy PDF. This is the Pixel Game Engine Handbook. It is currently being developed, so it's not actually complete, but it will do for telling us all the draw functions that exist inside of the Pixel Game Engine. I will leave a link to this handbook in the description of the video. The Pixel Game Engine has a lot of drawing functions that we can use, and if I were to just scroll through real quick, we can see what a pixel is and what it's all about. It talks about a couple of things that we're not going to go too much into right now, but we'll start looking at things we need from here. This handbook is really nice because not only does it tell you what the functions are, it also gives you some examples of how to use them. This means that you can see for yourself what something does, and if it catches your eye, then you can use it. So for example, this draw function draws a pixel on the screen, and as we saw before, we had a bunch of pixels on the screen. So, there are two versions of this draw function. It requests an x, y, and a color, or a position vector and a color. To keep things simple, we're just going to use the one that lets us put in an x and y position and a color value. So if I type draw, that's going to give me access to the draw function. In Visual Studio, this will also pop up with what you can type here. So we're going to use draw. In your editor, when you're typing, you'll get two arguments for this, as we saw in the handbook. And so we're going to type, let's put a pixel at position 5, comma 5, and let's just make it a black pixel. Actually, let's make it a white pixel. We have to put olc white because the definition of these pixel colors are in the olc namespace. Not something you have to worry too much about right now. If I were to run this program now, we would see one white dot slightly off the corner of the screen. In your game engine, the upper left corner is position 0, 0, while the bottom right is the width and height of your Pixel Game Engine. Let's look at that in a little more detail real quick. In the main function, when we created our Pixel Game Engine instance, we had these 4 numbers here. If I were just to mouse over this, it would show all the arguments for this function. 3 of them are optional, but the first 4 are not, and they pretty much define what our game is going to look like. It asks for a screen width, a screen height, and then the size of a pixel in width and height. So, just to give you an idea of what this means, I'm actually going to change the size of a pixel to 1 and 1. You might have noticed when I first ran this, the pixel was kind of large. You'll see here, the resolution of my screen is actually really, really large. So, if we made the pixel size 1 and 1, you can see, you might not even be able to see, it's very hard, a little tiny white dot there. If I were to scale the window up, we would start to see it better, because it's now going to zoom in. Essentially, if you want your pixels to be embellished and larger when you start, you can run this Pixel Game Engine with a larger pixel size, like this. And even though we specified the window to be 256 by 240, it's going to expand it to 4 times the size. It's more of a convenience function. And it makes all of your pixels be a certain size. Well, that's great. We can make a pixel. But I don't think that's going to necessarily help us for making the game Pong. Let's talk about the game Pong real quick. Hopefully you're already familiar with the game Pong, but it usually consists of a player with a paddle on one side, usually represented as a rectangle, and the enemy paddle on the right side. And then usually in this game, you have a ball represented with a square, or maybe a circle if you want to be fancy about it. And then in the center of the field, you might have, say, some kind of barrier here. And the barrier is actually not something that the ball will collide with. It just lets you, it's just kind of in the middle. To let you, kind of representing like a volleyball net or some kind of net. It just lets you know, hey, the ball's on your side, the ball's on the enemy side. It's more of a visual type of thing. But let's focus on the ball for a second. The ball will exist somewhere in the game. And when we talk about things existing in the game, uh, they usually have an X and a Y coordinate. I need to stop filling in my stuff. So this ball will be somewhere in the game. And so let's say it's at position 200, 200. That's roughly where it is if we started from the upper left corner where we said that was 0, 0. And then, I don't know, let's say the bottom right will be 600, 480. Actually, let's do 640 by 480. That's a pretty typical size, I would say. So we're going to design our game to be a 640 by 480 game window. So let's change that down here, where we say the window is going to be 640 by 480. We can run that real quick to verify that's what we want. And indeed, we get this pretty large window. We can't actually see what it looks like right now, but you can see my window went full screen because, well, we're covering that entire area. So let's try and make a ball now. The Pixel Game Engine has the ability for us to draw rectangles and circles. Let's use a circle to represent the ball. So following this, the draw circle function requires 3 arguments and has 2 optional ones. I'm going to draw the circle at position 200, 200 like in our example for now. The radius is how large the ball will be in one particular direction. And if we were to look at the handbook, it also mentions the X and Y position is the center of the ball. So the radius will be going outwards from the center. Let's do a radius of 20 for now. This would mean it has a diameter of 40 pixels. So the entire ball is 40 by 40, going 20 pixels around the center point. Let's just run this real quick and see what it looks like. So here we have our ball. Like I said, it's 40 by 40 in our game engine size. That should be fine. Maybe that's a little too big. I'll divide it by 2 and make it 10. We can also color it. I used blue in my drawing, but I think I'm going to make it yellow. Now, the ball itself is going to be moving, and we know it's going to be moving. So we don't necessarily want to use numbers. We want to use something called a variable. And in programming, or in game development in general, you're going to be using lots and lots and lots of variables. If you get stuck on a particular problem, it's probably because you don't have a variable for it. All of these numbers that get hard-coded, we call them magic numbers. And magic numbers can be dangerous because you have very little control over what's going on when you manually type in these numbers. So instead, if you use some placeholder to represent them and you change the placeholder, then it's easy for you to manipulate what's going on in the game. Let me explain that in a little more detail here. Our position 200, 200, while yes, that's where the ball currently is really the ball's X and Y coordinate. And we should have a way to represent what the X and Y coordinate is. So instead of saying it's at position 200, 200, we say it's at position X and Y, or let's be a little more specific here. The ball's X and Y. Ball X and ball Y. Then, let's say in computer memory, we're going to store ball X and ball Y somewhere, and we're going to have them equal to some value. So in computer memory, we're going to store these numbers. Numbers in computer memory is usually represented as what are called integers, numbers without any decimal value. And so for our ball X and ball Y, this will work just fine. Let's go ahead and implement that. Int is short for integer. Now, where we want to put this is based on how we want to use it. For now, let's just assume that every single variable wants to exist inside of our game engine. So, if we look at each of these functions as defining something in our game engine, then adding more stuff into our game engine would just put it at the top here. By typing int, which is short for integer, we can now create new values. Every single value we create needs to have a type at the beginning. So in C++, you write int followed by the name of that integer. Now we haven't assigned a value to it yet. You can assign values to things by using an equal sign. In our case, we're going to start the ball at position 200, 200. You'll notice now we have the number 200 in multiple places. This is usually a good sign because it means you have a direct replacement for those numbers. So, while draw circle asks for an x and a y position, we are going to give it numbers, but the numbers are stored somewhere else in memory under those variables. Let's take a look now. The circle's still at position 200, 200, but now it's also stored in variables. And now we're going to see why that's good for us. Let's say we wanted to move the ball. As I mentioned before, the user update loop happens on a loop. Every single moment, your game engine's going to try to run this loop as fast as it can. So let's try something simple. Let's make it so our ball moves to the right. Let's just make it move to the right. Try to get something moving here. In order to move something to the right, the positive x-axis is to the right. So, if we want to move something to the right, we have to move in the positive x-axis. So we would increment the ball's x position by some amount. Let's just try to add 1 to the ball position for now. There are two ways you can easily add to variables. The first is to say ball x will now become ball x plus 1. You can imagine this kind of like if the previous ball x was 200 and you said ball x equals ball x plus 1. Well, if we were to substitute those numbers into those spots, we would get 200, right? Well, we would get ball x is now equal to 200 plus 1, giving us a new value of 201, and that's going to be written back into memory there. So that's what that means. There is a short form of this as well. It's called the plus equals operator. Plus equals operator just does the same thing as this right here. Exactly the same thing. There is another short form, but I'm not going to explain it right now because it's not very important. So I'm actually going to use the shorthand here. Ball x plus equals 1. This means add 1 to the ball's x position. Let's take a look. And remember, this is run in the update loop, so we'll see it zoom across. Oh dear, what have we done? Well, we did see it zoom across for a very brief moment, but it's also left a streak behind. In a lot of game engines, when you draw something on the screen, it kind of just stays there. So every time, imagine this ball was drawn. First it's right there, and then I go ahead and draw it again. Now it's right here. And then I draw it again. And now it's right here. And you can kind of imagine or see what is happening here. Every single frame we're drawing a ball further down the line. But we're kind of forgetting something. We need to do what's called clearing the screen. So every time we move the ball, we actually want to first delete what was originally on the screen, and then redraw our ball at a new position. It would say it was here before, now it's here. That way, we're not seeing many copies of our ball dragging across the screen. For the Pixel Game Engine, that's done with what's called a clear function. The reason why you didn't see it in that crazy pixel example is because the entire screen was filled with pixels. But since we're not drawing to every single position on the screen now, we need to add in this clear function. Luckily, in the Pixel Game Engine, it's just called clear, and it asks for a color. So in this case, I'm going to type olc, and I'm going to clear the entire screen. I'm going to use very dark gray. I think that's a good color for our screen. So, if we just read what's going on here, we're going to clear the screen, move the ball 1 to the right, and then draw the ball at that position. Let's run it again. Well, we definitely don't have that yellow streak anymore, but it's kind of fast. And indeed, it is very fast. In order for us to slow things down, we gotta talk about elapsed time. In most game engines, every time the game updates, or your computer updates, it's going to take some amount of time, right? However, computers aren't on a strict clock. What I mean by that is your computer might be doing other things in the background. It might be slow, it might be fast. If you have a really fast CPU, your computer's update rate might be something like this. Boop, 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 boop. These dots just represent how fast your computer is updating. But let's say you had a slower computer. Then the update rate might be something like this. Boop, 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 boop. It might be a quarter the speed of another computer. And so the concept of elapsed time is how much time is passing from one frame to the next. Let's use some example numbers here. Let's say 0.1 seconds have passed. Now your computer runs way faster than 1/10 of a second per update. This is just a very exaggerated application of this. But the slower computer, every update is 0.4 seconds, 4 times as slow. This is a problem for us because if we're calling that update function 4 times slower, here's our update function. If we're calling that update function 4 times slower, that means our ball is going to move 4 times slower than somebody else's computer. And this is the concept of the elapsed time variable. The elapsed time variable lets us know how much of that time has passed. How do we use that value? Well, the elapsed time value is going to represent the amount of time that has passed in seconds. Now let's say 0.1 seconds have passed. Then elapsed time is going to be the value of 0.1. At this point, I'll also say that this is represented as a float, and a float is a decimal number in C++. So this is why we can use a decimal here instead of the integer we were talking about earlier. So if our elapsed time value is 0.1, what does that mean for our code? Well, here's our ball. Let's say we wanted the ball to move. Now we're going to represent the ball as a speed. Let's move it 50 pixels per second. This is a reasonable speed. I mean, if our entire game field is 600 pixels large, then it would take exactly 12 seconds for the ball to get from the left side of the screen to the right side of the screen. It's pretty slow, but it'll be a good example. So we want to move the ball 50 pixels per second across the screen. And the game engine is telling us how many seconds have passed for this update function. So, since we know how much time has passed, and we want to move 50 pixels per second, the math behind this is to take the 50 and multiply it by the 0.1. And your end result is 5 pixels. This tells us how many pixels we have to move in that frame. And this makes sense because let's say our computer was constantly updating at 0.1 seconds. Well, if we do this 10 times, what do we get? We get 50, which means our ball is indeed moving 50 pixels per second. So this variable is very important, and it's a concept a lot of game engines implement because when you are trying to run your game, you want to run it as fast as possible, but that means you have to account for computers that are faster and computers that are slower. It's kind of a weird concept, but it's how it's done. So let's go back here. So our target speed is 50 pixels per second. I didn't really explain this before, by the way, but these double slashes allow you to put comments in your code. The compiler ignores them. They're just for us humans. So move the ball to the right at 50 pixels per second. So I'm not going to just put 50 here. I'm going to put multiplied by. Now we don't put 0.1 here because the FE elapsed time can vary. So instead of 0.1, we're actually going to substitute that for our FE elapsed time variable. 50 times FE elapsed time gives us how much we should move our ball so that it moves 50 pixels per second. Let's run this real quick. Oh no, our ball doesn't move. What went wrong? Come on, Sig, you told us that we had to multiply by FE elapsed time. Why doesn't it work, huh? The problem is kind of hard to explain unless you know internally what's going on with the variables here. So what is going on? Well, if you remember when we started, we said we wanted our ball to be represented as an integer, and this is actually the reason why this doesn't work. Our ball position cannot be represented in fractional values right now. You're not allowed to have decimals in an integer value. So what happens when, let's say our game engine, our FE elapsed time value is like 0.0003, just some random value, right? Well, 0.0003 for 1 is a very small number. I'll pull out the calculator real quick and we'll look at that. So let's say if we're trying to move 50 pixels per second and we have to multiply it by 0.0003. Well, we're going to get a value of 0.0015, right? At least according to the calculator we do. So since we moved by 0.0015, well, let's add that to our ball x position of 200. We get the value 200. Wait a second, that's not how you do math. That is how you do math in the integer world. Integers will truncate all of the decimals. And since it truncates it, all you're left with is the value 200. That's why our ball doesn't move. That's the technical explanation. So how do we fix this? Well, we need to store those decimals. So we're going to change the ball x and ball y to be floats so that they are indeed decimal numbers. And this way, Now we can accept very tiny numbers here. And yes, my computer is really fast, so it's expected that that FELAPS time value is small enough to where we are getting zeros constantly. You can now see my ball is slowly moving to the right, which is about what we expect, 50 pixels per second. Excellent. So we now have a moving ball. That's quite a bit of work just for a moving ball, ain't it? Well, this is game development in a nutshell. Game development is very challenging. It's probably the hardest thing you can do. But it's a lot of fun learning it. Alright, so what's next? We have a ball. We moved it to the right. Let's talk a little bit about the paddles and player input. Let's get some paddles drawn to the screen first. We're going to be using the fill rectangle function, which we saw a little while ago, which draws solid rectangles. We're going to be using this version of the function. It accepts an x, a y, a width and a height, and an optional color. I'm just going to add them in right below where our ball was drawn. Let's put the player paddle somewhere near the edge of the screen. If we know the left side of the screen is position 0 in the X position, let's add like 20 pixels to that. And let's start the paddle somewhere in the center of the screen. Now, a lot of people when they're starting out programming, they usually just type in a number here. They're like, 200 sounds good, 300 sounds good. But hold on, we can be a little smarter than that. We do know how large the field is in terms of height. And luckily, our game engine also provides a way to tell us what the current height of the screen is. And you will find that these mathematical calculations happen quite a lot when you are designing your games and positioning things. Here's an example paddle again, and we're going to assume that this line right here, this imaginary line, is the middle of the screen. In order to center something, you need to first... I'm going to delete that real quick. First, you need to calculate what the center of the screen is in terms of the height value, the Y position. Now, we can just type in some number here, or in our case, we knew that the height of the display was 480 pixels. So we already know it's 240, right? But our game engine does know the height as well and stores it at what's called screen height. So since this value is stored in screen height, we can actually represent the middle of the screen using based on screen height instead of this number we put here. And why would we want to do this? Let's say we decided, oh, I want to change the screen height to be 520. Well, now you gotta look everywhere in your code where you used to write 240, and now you have to change it to 260, because that's now half of 520. As I said before, you want to get in the habit of working with these variables early, so you can avoid this. And that's why I'm trying to emphasize that the screen height variable already exists. We already said that the middle of the screen is half the screen height. And division in in computer programming uses the slash symbol. So we're going to be doing the screen height divided by 2 to represent where the Y position is. You'll notice I didn't draw the rectangle paddle in the middle of that line though. What we really want is the paddle to be here, right? But right now it's down here. And I did that intentionally. When stuff gets drawn on the screen, the origin point is actually the upper left corner. So if I told it to be drawn, let's just say this is at position x 300, and the y position is screen height divided by 2, as we already derived, right? If that's our position, then the center point will have to be calculated by taking half the size of the paddle's height. Kind of see where I'm going here. Let's say we made the paddle height, let's use a different number. Let's use 100, right? Well, if we wanted to center the paddle along the x-axis, we have to move it up by half the paddle's height. And when we do that, we end up with a paddle. Not like that. I cannot undo anymore. We end up with a paddle. That's not good either. That is basically centered. Like so. That's the concept anyway, but you'll see we need the paddle height divided by 2. That's how much we have to move it up by. So we can now change this formula to be the screen height divided by 2 minus the paddle height divided by 2. Whatever that is supposed to be. That should be our y position where we draw that paddle. And using the centers of objects is usually a good idea because it's easier to think in that way. If the ball is above you or below you, you want, like, most people, like, let's say the ball was here, right? Would you say the ball is above this paddle or below it? Most people would say it's above it right now, right? Because if this was the center of the paddle, most people would think, yeah, the ball is up here, so it must be higher than it. But if the origin point was in the upper left corner, then that wouldn't be true for your game engine. The ball would in this case be below your paddle, even though you think it's above it. So, for the sake of us humans, it's actually easier to think of the center as the origin points of objects in most cases. But in order to do that, we have to do a bit more work to derive where to draw things on the screen. There's lots of ways to make this easier for us later, but right now, since we're just discussing the basics, we're trying to derive very simple math formulas for how to get, like, the center of things. In any case, let's work on trying to implement all this now. I am going to use a float for this, and I am going to make a variable for the paddle x position as well. That way we can change it if we want to. We said we want to draw it starting at 20, so I'm just going to make it 20 for now. The paddle y position we'll make, say, screen. Well, I would use the screen height, but the game engine isn't made yet. And what I mean by that is anything you define up here is initialized into game memory before the game engine is created. So once the game engine is created, onUserCreate will be called. So we actually have an instance where we do want to set up the paddle y inside or after the game engine has been created, because then the game engine will know what the screen height is supposed to be. So here, we're actually going to say the screen height divided by 2. Yeah. Okay. So now, we can actually fill these in with the paddle x, and following along with our little diagram here, the y position is actually going to be the screen height divided by 2 minus the paddle height divided by 2. screen height divided by 2, which actually is our paddle Y right now, by the way. So we need to say minus the paddle. This is not the place for this. Minus paddle height divided by 2. We didn't actually make a paddle height yet, so we're going to do that now. I think it would make sense to also make a paddle width at this point. That way we can just fill it in. Let's make our width be 30. And then we have paddle height is 100. Now so far we have paddle X, paddle Y minus paddle height divided by 2. And since the paddle Y is at the screen height divided by 2, we already know that filling that in will give us the paddle exactly centered in the vertical axis. We can do the same with the X position to make sure the paddle is centered along the horizontal axis as well. I'm trying to leave some spaces here, keep things nice and tidy. The next two values for the fill rectangle is the width and height of the rectangle. And we already know those. Those should be the paddle width and the paddle height. Finally, we can define a color. I'm going to go with the green color for this paddle. Let's just run it and see what it looks like. There we go. We have a paddle where the center is now in the middle of the screen, and position 20 is about where my cursor is right now in the x-axis. So we have successfully drawn a rectangle that is centered along the paddle X and the paddle Y. And this is a generic algorithm for centering anything, by the way. You take the X position of it, you subtract half the width, then you take the Y position and you subtract half its height, and then you draw it with its total width and total height. And that will draw a paddle centered at the paddle position. In Pong, we actually need two paddles, one for the enemy paddle as well. Ideally, I would like to use a similar system, and so instead of paddle, let's make more variables and call them enemy paddle, like so. And we'll kind of do a similar thing for the enemy paddle, using similar variables. So we'll start the enemy paddle in the center of the screen again, and we'll also draw an enemy paddle. So I'm going to multi-select all of these. In Visual Studio Code, I hold down the Alt key to multi-select. I believe it's the same for Microsoft Visual Studio as well, so this can be very handy. I'm going to type enemy paddle, and then I'm just going to update these variables. You can see they have red squiggly lines because these variables do not exist. An undeclared identifier, which means they are variables that definitely don't exist right now. I'm going to fix those. And so we have an enemy paddle. Let's make the enemy paddle dark red. Let's just have a look at that. Oh, before I do that though, I just realized I made the enemy paddle X be 20. If we were to follow our, if we were to do this mathematically, we know that the width of our screen is 640, like internally, but again, there's a variable in our game engine to represent the screen width. So we're actually going to use that value and say, that way both the player and the enemy are equally spaced out. Since we made the player paddle 20 pixels out to the right, we want to make the enemy paddle 20 pixels out to the left from the right edge of the screen. I think that makes the most sense, and more or less is what we would want. So deriving the X position off of that, we're going to end up with, screen width minus 20 for the X position. And of course, the Y position is what we had before, enemy or screen height divided by 2 minus the enemy paddle height divided by 2, which should be the same. I don't expect that we want to give the enemy or the player a larger paddle compared to the others, but leaving these as variables makes it easy for us to change it later. So again, we will get errors, or just to show you real quick what happens if you try to do this, by the way. If we do screen width minus 20 to place our enemy paddle there, if you were to run this, well, you can see that it does run, but this is definitely not 20 pixels from the left edge of the screen. And that's because when this was originally created, it used some other value. Until the engine has been fully initialized, we can't use screen width or screen height because those values might change internally. So down here, I'm going to initialize the enemy paddle X to be screen width minus 20, where we actually want the paddle to be located. So far, so good. We have 2 paddles, and we have a ball. Now, obviously, nothing interacts right now, and the ball just goes through the paddles. So now let's talk about the game logic itself. Actually, how about we make this paddle move first? Let's talk about player input. Inside of the game engine is the ability to accept keyboard input. The way to do this is to say if key, get key. Got ahead of myself there. If get key, and it wants a key, as you can see, type olc, and we can get a list of keys. It kind of shows up here, they're kind of scattered, but there's quite a few keys we can choose from. For now, I'm actually going to use the arrow keys. Those are pretty typical. Let's say we want to do the up key first to move up. In the Pixel game engine, you would type a dot after get key, and you would say you got these 3 values here. They're all booleans, that's why there's a B in front of them, and you can choose between checking if they're held, if they are pressed, or if they're released. Just to really quick cover what that means, whenever a keyboard key is pressed down, there are 3 stages that occur. I'm going to use a line to represent the states of the key. Every key has 3. This yellow line represents the released state, the blue line represents the held state, and the green line represents the pressed state. The moment you press the key, the value gets triggered, and then a step later, it's nullified again, back to 0. In the held state, after you press a key, or the moment you press a key, the held state activates, and as long as you hold down the key, it will stay active until you release the key. The release state only occurs the moment a key is released, so at the very end of the states here. So depending on what you're trying to do in your game, you may only have to listen to the press event. The press event means the moment I press something, do it, but on the next set of frames, it's going to be off or false. In the held state, as long as you're holding down that key, no matter how long you hold it down, you'll be able to process that state and keep doing something. In our case, if we want to move the paddle up, we want to be using the held state, because as we hold down the key, we want the paddle to keep moving up. Of course, when we stop pressing the key, we don't want it to hold anymore. So the held event is perfect for our situation. But I think it was important that I at least explain the differences between the three. So, let's talk a little bit about what this means. It's pretty clear to see that if means we are going to check if something is happening. So we're saying if this key is held, this up key, then we're going to do something. In programming, this is called a condition. A condition works by saying if specifying a conditional expression which evaluates to either true or false, and then taking some action within. True meaning, yes, this statement is indeed true. That's what the Boolean returns. Or false, meaning no, this is not true. If we're not holding down the key, don't do anything. Ignore this statement. We also put these curly braces afterward. They are only optional if you have one statement. We're going to always put them, as it is good practice to do so anyways, in terms of code readability. Some folks like to do this, and as we write more complicated conditional expressions, you'll start to see these. This means is equal to. There are also some other conditional operators, which I will show real quick. Double equals is equal to. You have greater than, less than, greater than or equal to. I'm not drawing faces here. This is the greater than sign with an equal sign following it. Greater, less than, greater than or equal to. And less than or equal. There are also some other ones, more obscure. This one's also important. That's an exclamation point. Not equal to. Depending on what you're trying to do, you may end up combining these. But in our case, we want to see if the up key is held and that statement is true. However, usually the double equals true is optional. This and this are the exact same thing, so whatever you prefer. But to me, it reads better this way. If the key is held, do something. It makes sense. So when the key is held, we want to move the paddle upwards. Upwards is in the negative y direction. It's inverse of math. If you've looked at mathematical graphs, I don't remember what the graph system is called, but the y coordinates go down in there, or go up, not down. So as your y value increases, you would plot points higher up in the graph. In game engines, they go down. That's just the way it's always been. So to go up, we have to go negative. We already have a variable that represents what our paddle's y position is. So when we say we want to move up, we want to move that paddle y position in the negative direction. Again, we can do this one of two ways. We can say paddle.y minus some variable. Let's just say 1 for now. Or we can say paddle y minus equals 1. Earlier, you'll notice that we used plus equals to increase. Minus equals is the opposite, decrease. In this case, I like to use the decrement operator, minus equals. So subtract 1 from paddle y. Again though, we're going to run into that problem where, depending on computer speed, this could be very fast or very slow. So we always have to tie our value to this felapse time variable, which means move the paddle up at 1 pixel per second. That sounds really slow, right? I think it does. Let's instead do 60 pixels per second. You can kind of think of multiplying by felapse time as representing your movements in speed in pixels per second. That's how I like to think of it. It's a pretty good way to do it. Let's test our game. I'm going to hold the up key here. You'll see my paddle moves up at 60 pixels per second. It feels a little slow, so I'm actually going to add even more to this. 120. And I think that should do it. About double the speed will give us a nice amount of movement. Let's do the same for down. I'm going to go ahead and copy this. So instead of up key, I'm going to do the down key. And instead of decreasing by 120, I'm actually going to do plus equals to increase the paddle by 120. I'm going to change the comment to say move the paddle down at 120 pixels per second. At this point, I'm pressing the up and down arrow keys, and indeed my paddle is moving along there. You can see we can move the paddle outside of the screen right now, and if I were to hold both arrow keys down, the paddle stops moving. You may be wondering why that is. And if we were to follow the logic here, we would say if the up key is held, move it down or move it up by 120 times felapse time, and then if the down key is held, we move it down by 120. So essentially, if we hold both up and down, both of these statements execute, and we get a net gain of 0 pixels in both directions. In any case, that gives the up and down movement for the paddle. This is actually why I recommended we put most of our stuff into these variables in the first place, because when you're dealing with games, you have a lot of objects, and these objects have these properties to interact with, and so if you have them all laid out in these variables, it's very easy to modify them to be whatever you want them to be. Okay, so that's great. We have a moving paddle. Next, we want to make it so we kind of have an actual game. We need to deal with collisions. And this is always where things get a little challenging, because collisions are frankly not easy. There are a lot of ways to do collisions, but I like to keep things as simple as possible. If you were to search how to make a collision system for whatever you want, like if we searched how to do collisions for Pong paddles, you'll probably get results where, oh, you have to do like the ball width minus the ball height, or the ball width minus the paddle width, and compare them and see what the distance is between them, or maybe something like, oh, you have to do this like rectangle algorithm. Here's the rectangle algorithm. This happens a lot if you start searching for these things. And to be honest, I try to discourage people from simply copying algorithms from the internet, and instead taking some time to actually understand what we want. So here I've got my paddle, and here I've got a ball. I'm actually going to make it a circle, because it is indeed a circle. That's pretty much what our game looks like right now. And we'll probably reverse the ball direction to go to the left, and then we'll try to make the ball collide with our paddle. The concept of colliding can be very simple in our case. The ball itself has a radius of r, and circle collisions honestly are one of the easiest types of collisions you can do. If you can do circle collisions in your games, then you'll be golden because they are so simple to implement. Now, when our ball's out here, obviously the ball is currently not intersecting the rectangle, but we can say the center of the ball, right, is the ball X and the ball Y. Our draw function was already drawing the ball in the middle, so visually we're good. If we want to see if the ball is colliding with the paddle, we actually want to look at the very edge here. And how do we get that edge? Well, in the horizontal plane, that would be the ball X minus R. So whatever the radius of our ball is, that's actually the yellow dot here. And then we have to see if it's within the range of this rectangle. Now we know where the position of this rectangle is. We actually drew it with the center point being the, what do I call this? Paddle X and paddle Y. So, once again, since it's centered, we need to take half the width to find out what this outer edge is. So, the rightmost side of this paddle is paddle X plus the paddle width. And guess what? Since we already wrote down or stored all of our numbers and variables, this makes it very easy for us to compare these two. So we already know what the rightmost edge of the paddle is, and we know the leftmost edge of the ball. So we can use these two variables to figure out if the ball collides with the paddle. Now there are some edge cases here, literally. We'll deal with those in a little bit, but this is the basic idea behind a ball collision. We're going to see if ball X minus R is less than the paddle X plus paddle width. And right now, I have these as very long-winded variables. We're actually going to simplify this a bit. This will be called the ball left. And then I'll call the right side of the paddle right. And that makes it simpler for us. So we could say if ball left is less than paddle right, then at least we know the ball is to the left of the paddle, right? It can technically collide with it. We just have to do a couple more checks within the vertical axis to determine if that ball is then touching the paddle or not. But this is a good start, and I think we should implement that first. So as I said before, we first want to calculate a ball left. And we're going to be doing this inside of the onUserUpdate function. We're going to have like a collision section where after the ball has moved, let's determine if the ball has collided with the paddle. Also, I'm going to reverse this for now. I'm going to subtract the ball's position because I have a feeling that we want it to go left so we can test collision with our player paddle. And you know what? This is kind of annoying to change, isn't it? I'm going to change this to be the ball. I'm going to say this is the ball's X speed. Because I think later this will come in handy. The ball X speed. So if I ever want to change it, I just set it there. But I'm going to make it plus equals ball X speed and make the ball X speed negative. I think it would be weird if it was inverted. So If we make the x speed negative 50, we're implying that's going to go to the left. If we were to make it positive, it would go to the right. We can test this real quick. Make sure it's now going the opposite way. And indeed, the ball is going the opposite way. Very good. So we're going to have a new variable called ball left. Now, as I said before, every single variable in C++ has to have a type following it. We're going to keep all of our positional values floats. In games, you're usually going to use decimals to calculate everything. So we're going to keep using floats here. So float ball left. And we said ball left was the ball x position minus its radius. Unfortunately, we don't have a ball radius yet. So we're going to make one. You're starting to see already how many dang variables we have, and we're only implementing 3 objects. And pretty soon, we're going to be talking about how to group all these variables together so it's less of a mess like this. But for right now, for simplicity's sake, we're going to keep creating these variables. It's good to get in the habit of doing so. The ball radius, I think, was 10. I'm going to set to 10 here. And because we are putting in a variable, you can see down here, again, we have a hard-coded 10. I'm actually going to change this now to be ball radius. So ball left is ball x minus ball radius. That is indeed what we wrote inside of our little notes. Next, we need the paddle right. So let's get the paddle right position. Paddle right will be equal to the paddle x position plus half the width of the paddle. And then we said if ball left is less than paddle right, then we might have a collision. There are a couple of exceptions to this, but this is the basic idea. We need a way to know that the collision has occurred. I think the way I'll do this is, for now, is actually draw this ball in here. And the reason is I can make it be a red color if there is a collision. Otherwise, I can make it a yellow color. I think that would be a good idea. We can use what's called an else statement to further extend our logic. And it kind of reads, if we have a collision with our ball, then we're going to draw it with a red circle. Else, meaning if there is no collision, we're going to draw with a yellow circle. That's what this else statement is. And again, you do need braces around it. They are only optional if you have one statement. But even though we have one statement here, I think it's a good habit to get into anyways. You can see here, the moment that ball got to here, it actually turned red. We'll watch that one more time. Excellent. So you can see with a little bit of preparation with our drawing, or our some math calculations, more like positioning, we have an accurate collision system for the ball at least. You notice I said if we collide with the ball, but right here we're writing if ball left is less than paddle right. That's not very intuitive, is it? In the future, we will make it actually read properly. If the ball collides with the paddle. You can solve this by using functions. Unfortunately, functions are a little hard to grasp when you're first learning them. I'm not going to complicate it too much and just focus on the logic right now. So just know that even though right now it might be a little hard to read this and keep remembering, yeah, this means the ball collides with the paddle. There is an easy way to fix this in the future. We just need to spend some time talking about functions. I think that's better suited for another video though. So this works, right? Well, not necessarily. Let me show you why. Let's instead move the paddle Y while the ball's moving towards our ball. Because remember, we can move our paddle. As you can see, even though we clearly moved the paddle above the ball, it turned red. Now, it was technically in collision with the paddle if the paddle was there, but that's because we only handled the X direction. Let's now talk about the Y direction, and this is the second part I was talking about, why we had an edge case here. Let's actually use the previous diagram. I'm just going to erase a bunch of stuff. So you might imagine now that we're going to be using some y-coordinate stuff. And indeed, you would be correct. Wow, I basically erased everything. Should have just started over. Alright, so here's our paddle, once again. Here's our ball. That's not a ball. Once again. Center point, and our radius system. Because we know every circle has a radius. So, what are we going to do now? Well, let's use our example case I made earlier. The paddle's now up here. And we're going to be dealing with the y-coordinate. So, if we drew a line straight up in our circle, we now have the topmost and the bottommost points. Of course, it would be the same length, just going downwards, R2, which is also R, so to make it less confusing, this is still R. So we have the top point and the bottom point, and we can calculate those once again. That position is at ball X, comma ball Y, minus R, because minus means we're going up in the y-axis. Ball X, we can represent this as ball Y plus R. And so now we have, again, we're going to make a name for these. Just like I called the other one ball left, we're going to call this ball top, and this is ball bottom. The next thing we have to look at is the Y position of the paddle itself. So again, the paddle starts with its center point of origin there, and then to find out the top and bottom points of the paddle, we have to look at the paddle height, but divide it by 2. And I just deleted it. Very good. Oops. My bad. It's now a fat paddle. That's not a line. So once again, we need the paddle height divide by 2 to figure out where the top and bottom points are. Paddle top and paddle bottom are calculated similarly as paddle X, comma, paddle Y minus the paddle height divided by 2 and for the paddle bottom, paddle X, comma, paddle Y plus paddle height divided by 2. With that all figured out, we can now make some logic for figuring out if the ball is going to collide with the paddle. So we have to do 2 checks. First, we have to see if the top of the ball is less than the bottom of the paddle. So if this point is less than this point, like let's say it was down here, right? Then yes, if the red point was less than the blue point, then we know for a fact that it is going to be along the vertical axis within range. The second check is to see if ball bottom is greater than the paddle top. That's a whole different scenario. What if we had another paddle, but it was down here? Well, we have to see if the bottom, the ball bottom, which is this red dot, is further down than the top point. So if the top point was here, then no, this ball is clearly out of range. But in this other paddle, the top point is way up here, and so the ball bottom is way down here, and indeed, the ball bottom is greater than the paddle top by a long shot. So with these two conditions, we have now defined what it takes to be vertically colliding with a paddle. So once again, we will implement this similarly. First, so we already handled horizontal collisions. Now we have to combine it with vertical collisions to once and for all determine if we are indeed colliding with the ball or the paddle. If the paddle is colliding with the ball. So let's start by defining a ball top. Once again, the ball top is calculated by taking the ball Y position minus the ball radius. The bottom position is calculated by adding the radius instead from the center. And then we also have the paddle top. I'm going to separate these a little bit. These are related to ball horizontal checking, collision checking, while these ones are related to ball vertical collision checking. The paddle top, very similar in structure. It's the paddle Y minus the paddle height divided by 2. And for the paddle bottom, it's the paddle Y plus the paddle height divided by 2. Ooh, that's a lot of stuff, ain't it? Now we have to combine them with this current statement, which means we have to talk about conditional operators that allow us to combine logical statements. Let's talk about that real quick. There are a couple of these. They're usually called logic gates. You've probably seen some of these if you've done, like, I don't know, redstone logic in Minecraft. Or if you've done electronic circuits, you've definitely seen logic gates. These are some of the basic ones. Not. And we'll talk about, we're going to be specifically using AND. In programming languages, you would typically use certain symbols to represent these. So up here, AND is represented as 2 ampersand symbols, or would be represented as 2 vertical bars. The bar on your keyboard is typically found right below the backspace if you have a standard American keyboard. You usually have to hold shift to type them out, but they're vertical bars. XOR is typically done with a caret operator, and NOT is usually done with an exclamation point. And the meaning behind these is they produce different results based on two conditional expressions. Remember that conditional expressions can be either true or false. So in our case, this helps combine two conditional expressions, and depending on what both of these are in combination, it produces a final resulting logical logical answer from it. So it's kind of like conditional math. In order for the AND gate to work, both inputs have to be true. True and true returns true. While if either of these are false, or if both are false, then the result will always be false. False and true is also false. Or is a little different. Or means as long as one is true, then the result is also true. Oh, sorry, I put and again. Or, if we have false or true, then we also get true. These are it's kind of gee whiz information for now, but XOR means only one of these can be true. If they're both true, you get false. True XOR false, you get true. And if they're both false, you get false. Not simply negates the operator, and it's not actually a conditional operator. It simply just negates it. So if the input was true, then your output is false. And if your input was false, your input becomes true. This is important because in order for us to evaluate our collision here, we have to see not only is this X collision, where's the X collision? Oh, I erased it, I forgot. Oops. But in our code, not only does this X collision have to be true, but the Y collision, which there are two possible values here, both of those have to be true as well. So in other words, we're going to be using AND. Typing double ampersands again means AND. And I'm going to break it up into a bunch of lines here to make it a little easier to read because there's quite a bit going on here. So we're going to follow what we wrote here. We're going to say if ball top is less than paddle bottom and ball bottom is greater than paddle top, and of course ball left is less than paddle right, then that means the ball has collided with the paddle. Let's have a look. First, let's just make sure it still works like this. Indeed it does. The ball turned red. Now I'm going to do it again and do the test I ran before where I move the paddle up here. As you can see, this time the ball did not turn red. This time I'm going to skirt the ball so we can kind of see it as I move down. You can see it started red and then I moved down out of the way and it stopped being red. So indeed, we have come up with a mathematical way to describe a ball to paddle collision. And at first it might seem a little intimidating to do this, but if you stick to rectangles and circles and you learn how to do these types of collisions like this, it is very easy to make collisions for your entire game. And in the future, I will be making easier ways for us to define collisions between two objects. We're just at a basic level where we're trying to get something working here. So this is all well and good, and we've done this for one paddle. What about the other paddle? Well, we gotta do the same thing. but for the other paddle. And of course, when we collide with the ball, we don't want to just... Right now we made it turn red as an indicator, but that's not actually what should happen in the game, right? I'm now going to move this back out to here. Just draw the ball as a yellow circle. I'm also going to get rid of this part. When the ball collides with the paddle, we actually want it to bounce off the paddle and reverse direction. Well, how do we reverse the direction? We have to change the X speed from going to the left to going to the right. And guess what? We already represented which way the ball was going using ball X speed. We started as -50, which made it go to the left. So, if we collide with the ball, all we have to do is make the ball X speed now go the opposite way. We're going to make it equal to 50. A fancier way to write this would also be to say ball gets multiplied by -1, the inverse. I think that could be a little confusing though, but it's another way you could do it, right? If you multiply a number by -1, it flips the sign. But I think this is a little more intuitive. We're just going to make it go to the right if we detect a collision. So let's see that. So you can see right at the moment the ball hit the paddle, it reversed its direction and is now going towards the enemy paddle. So now we have to make a collision for the enemy paddle and make it do the same thing. So let's do that. The enemy paddle uses variables called enemy paddle instead of paddle. So if we were to do some find and replacing, this should be pretty easy. We don't have to duplicate the ball variables because, well, the ball is the ball. There's only one ball. So we don't have to worry about that. So with a little bit of copy pasting and replacing, we can then make some variables that represent the enemy paddle. And now we can also do some copy pasting, but for the enemy paddle condition. And if it collides with the enemy paddle, we just reverse it. Since we already figured out all the logic, it's as simple as doing a little bit of changing some values around. Oh, looks like we have a bug. What happened? Well, it looks to me that we have calculated it using the ball left position, so instead of the ball right position. Remember, the ball would be going to the right, not the left. And so currently it's trying to go from the left. I guess the easiest way to describe this is it's wrong. Because if we want to collide with the enemy paddle, which is on the right side, I wish I still had the diagram for that, but our enemy paddle is on this side. And if we were to use... If we were to use the left side of the ball, which we said, right, we were using ball left, that's what this point represents, and we're using enemy paddle right, well, of course ball left is going to be less than enemy paddle right. That is always the case, as long as the ball hasn't gotten to here, at which point now this point is indeed greater. So then it would be a collision. But that's not what we want, obviously. We want the ball right position to be, see if that is now greater than the paddle left position. So a little bit of tweaking. We just have to reverse which side of these we need to look at. And we don't actually have these variables created yet, so we're going to have to do that. So ball right will be the ball x plus the ball radius, while the paddle, enemy paddle right will actually need to be the enemy paddle left side, and then subtract from the enemy paddle width divided by 2 instead. Oh, and the sign needs to be flipped. There we go. So now we don't have these like conflicting things where it keeps the ball going in that certain direction. So now let's just make sure that when the ball touches the enemy paddle, it indeed goes back towards the left. As you can see, we now have a successful bouncing between the two paddles, and that's wonderful. However, Pong is usually a little more exciting than this. For one, the ball can also move vertically, making things a little more challenging, making the player having to guard against the ball. That's funny. We'll deal with that later. But not only that, the computer player should be moving around too. We'll deal with that last. But first, let's get some little more movement into the ball. So far so good though, we're making good progress. Since we already have an X speed, why not add a Y speed to our ball too? Let's make it 50. We're going to make the ball bounce around, so we're going to make it start by going diagonally to the left. In order to incorporate the Y speed, we need to also adjust the ball Y position by adding the ball Y speed to our current position. We'll also multiply it by elapsed time, because again, depending on... Move the ball vertically. I'm going to change this comment to move the ball horizontally. It's actually the reason why I hate comments, because comments make it so you have to change them if you update what's going on. They're good for learning though. They make you remember, yeah, that's what that code does. Let's just make sure the ball is now moving in 2 axes at once. And indeed it is. If I don't block it, it doesn't bounce off. As you might have noticed, the ball just ran off the screen. So we need to make something to make it bounce off the screen. Yay, more collision stuff. Alright. Well, as you can imagine, we're probably going to use similar mathematics to figure this one out. Here's the screen. And here's the ball. And again, it has a radius. And all we have to do, we already calculated ball bottom, right? So we just have to check if the ball bottom is greater than the bottom of the screen, which we have defined as the screen height that was provided to us by the engine itself. So if this Y position is greater than screen height, goes below it, we know we have to bounce off it. And how do we bounce? We're going to reverse the Y direction. We can do something similar for when the ball is up here at the top. We're going to use the ball top this time, which again is based off of the radius from the center. And the formula for this is if ball top is less than 0, because the top of the screen is 0 in the Y-axis, then again, we're going to reverse the Y direction. All right. So again, we have already calculated ball bottom and ball top. And this is all of our collision code. We're just going to put it right after here. So we'll follow our logic here and say, if ball bottom is greater than screen height, or, see, we can say if either of these statements are true, we're using that or now with the double bars there, or if ball top is less than 0, Then we're going to reverse the ball y speed. Now, I did talk about this earlier for the ball x speed. I think in this case, we're going to have to do a sign flip. So we can do ball y speed multiplied by -1. Again, there is a shorthand for this, multiply by -1, which is the asterisk equals, like so. I think that looks fine. You can format it however you want to make it easier for you to understand. And we'll add a little comment. If the ball touches the top or bottom edges, reverse its y direction. So let's have a look. You can see it just bounced off the top there. It's not going to quite collide with the enemy AI, but I think it might hit the top here, so we'll see it bounce off the top. Boop. And indeed it does. Excellent. We've almost got a pretty functioning game. So let's talk about the edges now. If the ball goes to one of the edges, let's just make it so the ball resets position for now. We can use a similar formula to this. It'll just be for the edges of the sides of the screen. So we're first going to see if the right side of the ball is greater than the screen width, or the left side of the ball is less than 0. I had to think about this for a minute. That's why, in my opinion, drawing these out is very important, and figuring out these mathematical formulas, because then you just have to copy them. Like, I'm literally writing the code almost word for word from the diagrams I made earlier. It's a very powerful tool. We're going to reset the ball position here. Let's write down a comment real quick. If the ball touches the right or left edges, reset the ball's position. And we'll do some more later, of course, but let's first reset the ball's position. The original ball's position was at 200, 200, but I think later on we decided we want it to be in the middle. I think that makes the most sense. So let's reset the ball to the middle of the screen. Ball x equals screen width divided by 2. Ball y equals screen height divided by 2. Let's have a look. I'm going to let the ball die. You can see it immediately goes back. Seems to work pretty well, I dare say. Watch it a little bit more. Now the ball is going pretty slow. In most Pong games, after you've hit the ball once or twice, the ball starts getting faster. You can see the ball reset there, just barely didn't hit the opponent's paddle. Let's make the opponent come to life. I think we have to talk a little bit about how the AI works, though. In its most simplest form, the AI needs to at least kind of follow the ball. Now, if you make the AI simply follow the ball, it might be too good, so we might have to add in some variation to that to make it so it's harder to win, or it's harder to lose against the paddle. Harder to win? Make it so it's easier to win, essentially. So yeah, let's say the ball's up here right now. Regardless if the ball is coming or not towards the paddle, we're not going to worry about that aspect for now. We want the enemy to generally be where the ball is going to be in the future, right? We want the AI to move up in this instance. So I've already marked the center here, and as you might expect, we're going to use those 2 points to figure out which way to go. We already have the center points, The center points of the paddle is paddle X and paddle Y. In this case, it's actually enemy paddle X and enemy paddle.y. I'm just going to put EN here to save myself some writing. And the ball X, of course, is ball X and ball Y. So we already know where these positions are. We just have to compare them accordingly. There are two cases we have to consider. If the ball Y is less than the paddle Y, it means it's above it. So since the ball is above the paddle, the AI wants to move up. And the other condition is if the ball is below the paddle, if ball Y is greater than paddle Y. In that case, let's move down. This at least forces the AI to move towards the ball at all times and gives us a nice starting point. So let's see if we can implement that. So this is all the collision code. I think we'll move the paddle before calculating any collisions, just like how we moved the ball up here. Actually, where do we detect where to move this paddle? We'll put it in the same place, down here. So this is how we move the player paddle. We'll give the enemies the same opportunity, because all the code is executed from top to bottom, right? If there is even a slight advantage to where in one frame your collisions might happen before you move, who knows, that could be considered an unfair advantage, right? It's just a really technical thing. We don't really care that much. So let's write this down. If ball Y is less than enemy paddle Y, then we want to move the enemy paddle up. So to do that, we can subtract a certain amount. Now, you can see when we held the up key, we were able to move at 120 pixels per second. I think since the AI is perfectly going to follow the ball, let's actually handicap it a little bit and say it can only move at 100 pixels per second, making us superior. That way the game, I think, will be a little easier to play at least. The other condition is to see if the ball Y is greater than the enemy paddle Y, in which case we want to move down instead by incrementing it. Let's take a look at that. As you can see, the enemy paddle is trying to follow the ball now. Exactly. It looks like it can keep up with it right now. But like I said, we're probably going to make it so... Oh, this is in the way. My bad. We're probably going to make it so the ball speeds up every time you hit it. We already have a ball X speed and a ball Y speed variable. So, I think we can use those to figure out how to speed things up a little. Let's get to it. I think the easiest way to do the speed up is to multiply both of those variables by some small amount. Like, let's say multiply it by 1.2 or something. I think that's a good number, right? Let's have a look real quick, just as an example. If X speed started out as 50, and we multiplied it by 1.2, after one hit, the speed will be 60. And then we multiply by 1.2 again, we end up with 72. And this can continue going and going until eventually it becomes too fast and one of the players lose. 1.2 might ramp up too quick. I think 1.1 might be better. But that's the theory anyway. So, right here and right here, we check if the ball collides with a paddle. So every time it does, right now we're saying X speed gets set to 50. And that's not quite what we want, right? We want to reverse the direction. So I originally hinted at using this. Now I'm actually going to implement this. We're just going to reverse the sign of the ball, so it's going the opposite way. And then we'll also increment the ball's X speed by multiplying it by 1.1 or something like that. If you really wanted to, you could combine these and say multiply it by the inverse of 1.1. And that will actually speed up the x speed of the ball, but not the y speed. I think we also want to speed up the y speed by multiplying it as well, just to make sure that it is indeed speeding up in both directions. Otherwise, it'll look weird. It'll be like zooming across along the x-axis, but not the y-axis. And finally, I think when the ball touches the right or left edges, that's a reset, right? So let's just reset the x speed and y speed to be back to normal, or as normal as we can get it at least. We'll say 50-50, like that. Maybe we'll randomize it a little later, but for now, I think that's good enough. Let's have a look. So once I hit the ball, it didn't get that much faster, but I think after we hit it 5 or 6 times, we'll definitely notice it's speeding up. And this is usually how the game of Pong starts out anyways. It starts off pretty slow, pretty simple, pretty chill. I can already tell it has indeed increased in speed, because the CPU is already lagging behind it just ever so slightly. So we'll keep hitting the ball until it goes faster and faster. It's about double its original speed now. Oh my god, what happened? It just zoomed, didn't it? Well, there's actually a problem with our code which I haven't talked about before, and I'll demonstrate it right here. If you were to like skirt the ball along the side here, you can see the ball just teleported a bunch. And that's because what I did was I intentionally let the ball go a little past my paddle, and then I kind of just hit it from the side. And then the ball like goes crazy and then resets. And the reason why that happens is because even though, yes, we have reversed the speed of the ball and set its increase the speed, if on the next frame it's still colliding with the pad or the paddle, then, well, it'll do it again and again and again and again and again. It's a pretty funny little bug, but it's obviously not what we want. I'll just visualize it with the diagram real quick for you. Here's a very zoomed in version of our paddle. And of course, we have a ball. We have part of a ball over here, because I'm really zoomed in, so I'm just going to make part of the ball here. As we approach the paddle or the ball from here, you'll already notice the ball is like quite a bit past the threshold here. Because remember, the positions we're checking for collision is the left side of the ball and the right side of the paddle. So there's quite a difference, like half a paddle's width of space. So on the next frame, we say, okay, yes, you have collided with the ball. So reverse the direction of the ball. So the direction of the ball was left. Now it's to the right with a faster speed. Okay, cool. So the ball moves at this speed, faster speed, a little bit to the right. And then on the next frame, it says, wait a second. This dot might be like here now. It's moved a little bit over, but it's still in range. So it says, I collided with the paddle. I'm going to reverse my direction even more and then go back this way. Uh-oh, we can start to see a problem, right? Now the dot is over here. And then it's like, wait, now on the next frame, I'm colliding with the ball again. So now I'm going this way. And this repeats until eventually the number is so high that the ball just zooms off of the screen. So that is what's happening in a very dramatic manner. What can we do about it? These kinds of problems come up all the time because games constantly like run. It's just every single frame stuff is happening, collisions are happening. This is where collision bugs can come up all the time, right? The easiest way to fix this is when we touch the ball, we make sure the ball is no longer in collision of the paddle. You'll find this with a lot of collision systems, right? If if you ever detect a collision, try to put the thing you're colliding with out of a collision state, so it never can collide on the next frame. That's like my biggest tip with collision systems. If you want bug-free collision systems, the moment a collision happen, make sure you get your game in a state where a collision will not happen on the next frame. In our case, in order to fix this, right? Let's go back to our diagram real quick. What I would do is right now our ball is heavily inside of our paddle. Well, just teleport it. Like I'm gonna overlay the ball here real quick. Just teleport it to be here. That way it's not colliding anymore, right? No matter how far in our ball is, teleport it back out so on the next frame it's not colliding with it. We always want to try to get our game in that kind of state. So, in order to do that, we have to make sure the ball's left position is no longer less than our paddle's right position. And the easiest way to do that is to just say ball x equals paddle right plus ball left. As weird as that sound, it does work. We can look at that here. This red dot right here, that's our paddle right. And right here is also our ball left. So if our ball's position was this blue dot in the middle here, we subtract, or we put the ball at paddle right plus the radius of the ball. So we'll say paddle right plus the radius, which is essentially the same thing, right? The ball radius, the ball size. Paddle right plus radius. That's what we'll do. I guess what I said the first time was kind of wrong. Paddle right plus ball radius. That makes sure that our ball is no longer anywhere inside of our paddle at all. We have to do the opposite for the enemy paddle. We have to put the ball X at the enemy paddle left minus the ball radius. Wait, the enemy paddle's left? Yeah, that's correct. That way it kind of teleports back into the spot it needs to be at. Oh, my game is on the other screen. Let's try that again. Alright. So go ahead and bounce it off. I'm going to try to do that trick again. As the ball approaches, I'm going to approach it from the side. This time, the moment I hit it, it's actually going to jump in front of my paddle here. That way we are only colliding with it like once. So I'm going to try and get in position for this. Boom. As you can see, at that moment, it immediately jumped a little bit. You can like see it kind of teleported. Also, we had a little bit of weird movement where the ball didn't quite bounce off the bottom of the screen. I have an idea why that might be, but let's do that one more time. You can see it kind of just bounces off there. That's more or less what we wanted. I think it works pretty well. Now that we fixed that bug, we more or less have a game. We're not keeping track of points though. So, I think it's time we did some point tracking. Now, the reason that that bug at the bottom occurred is kind of similar. You can see the AI can't keep up right now, so as long as we hit this, we should win right here. AI is too slow. Ball resets. Very good. One thing I will say is we kind of need to do the same thing. Snap the ball when we collide with the top and bottom. Right here. Because just reversing the Y speed, again, maybe the ball on one frame is going a little faster than on the next frame. Remember, computer speeds can vary. this could cause collision bugs. If we want to get out of a collision state whenever possible. So we're going to do a similar thing, but for the ball Y snapping. Right now we have two different conditions here. If the ball bottom is greater than the screen height, meaning the ball is below the bottom of the game, or the ball is above the top of the game, then we reverse the direction, but then we have to snap the ball back into the game field. So depending on which one is occurring, we have to actually do certain things. Let's bring up a diagram real quick for this one, because that's a little confusing, me just saying it like that. Yeah, let's just get our formulas again. We love our formulas now. Top of the Y screen is 0. Bottom of the Y screen is screen height. So we want to use ball top. And when ball top is less than 0, which we've already defined, right? Because we have an OR statement for that. Then we want to snap the ball to be make ball X equal to whatever the top is, which is 0, plus the radius of the ball. I put ball X there. Oops. Ball Y. So the ball Y becomes the ball radius, because if this is the radius, then we have to set the position exactly to the radius of the ball for it to be just at the top of the screen. For the bottom, we have the ball radius again, but we're saying when ball bottom is greater than the screen height, which we already have, then we're going to say ball Y is now equal to the screen height, but we're going to subtract the ball radius. And that puts our ball into a non-colliding state, which prevents collision bugs again. All right, so we'll do that real quick. Now, right here, I already have two if statements. So one way we could do this is to make these a little redundant. We just then do certain things for each of these conditions. That's what I was saying earlier. Because we know this happens, and one of these two statements is true, so depending on which one we do something. But this is a little redundant, and the better way to handle this so it makes more sense to us is to actually divide this into two if statements. So I'm actually going to take this guy and move it up to here, and then leave this one here. If the ball touches, in this case, this is the top edge, we'll have another one for the bottom edge. I just separated them to make things easier. In both cases, we are reversing the y speed, but then we're also going to set it based on this. According to our notes, if ball bottom is greater than screen height, we're going to set the ball Y position to be equal to the screen height minus the ball radius. For the top edge, we're going to set the ball Y to be equal to the ball radius. Again, this is to prevent a collision state after, well, a collision state. Always try to get your game into a non-collision state after a collision. This prevents your game from having collision bugs. Excellent. Let's get back to that scoring topic now. In order to keep track of score, we have to determine which side of the ball, or which side of the screen the ball ends up hitting, and based on that, award a point to the other side. We're also going to have to display how many points one side or the other side has. So, let's add two variables to keep track of our score. We have the player's score. We'll start it at 0. And these are integers, by the way, because we don't have to store decimal score. That doesn't really make sense. Then we have the enemy score, which we start at 0. Right here, we have the code for seeing if the ball touches the right or left edges. Again, just like with the top or bottom edges, these are currently combined. I'm now going to separate them for the sake of making it easier to figure out the logic for both. In both cases, we do have to reset the ball, so this code will be in both places. However, the score we assign will be different. If the ball collides with the right side of the screen, I'm going to write this. If the ball touches the right edge, award a point to the player. In the other one, the other instance, if the ball touches the left edge, award a point to the enemy. Then, it's as simple as assigning player's score and adding 1 to it. Plus equals 1. For the ball touching the left edge, we'll increment the enemy's score by 1 value. There's no point in me really running it, because we have no way to visually represent score yet. So let's make a way to visualize that. We need a way to draw text, and thankfully, the Pixel Game Engine provides us a way to draw text. Draw string. You can see there are many ways to draw some strings. And here's how we do it. You specify an X and a Y position, and some text. You can optionally specify a color, and scale the text. So, I think we want to draw the score pretty large. We want to draw them on the screen at certain positions. Those positions don't have to be quite exact, but we'll try to make them in good spots. So we're going to use draw string. For the X position of the player's score, I'm going to put it, offset it by 30 pixels from the left, 30 pixels from the top. The string we are drawing is actually going to be a number converted to a string. So this is a C++ function that you're going to have to look at. We're going to look at the standard namespace. So you type std : and then you type 2_string. And what this function does, as you can see here, it's asking for an integer, is it takes some number and it converts it into a text representation. You can't just, you might think, okay, let's just put player score here. The problem with putting player score here is draw string wants a string. So it says no known conversion from integer to string. So it's very confused right now. That's why this function called toString exists. By using that for a number, you can convert a number to a string. And strings are just a way to represent text in programming, like saying hello or goodbye. You can see in the example here, we just wrote a bunch of letters. And if we looked at the sample code here, you can see the text is wrapped in quotation marks. So if you want to display other text on the screen, like we could display a title of the game or something, we could definitely use these strings like that. And that's actually a good idea. We'll probably display the name of our game at the top of the screen in a little bit here. Let's draw the enemy score. Now, I want the enemy score to be in a similar spot to where the player score is, but in reverse. So I'm going to go ahead and use the screen width minus 30 and the screen height minus, or no, we'll keep the Y position the same, right? Just put it the X position on the other side. So if I do screen width minus 30, that does put on the other side. You can now see there are two numbers on at the top, but they're very small. I did say I wanted to make them larger. Let's just make sure it changes right now. I think that'll be good enough. And then we'll make them a lot larger so they seem like they are score numbers. Very important. You can see when the ball touched the left edge, the enemy gained 1 point. The number changed to a 1. Very good. So let's just make it so that they are a lot larger now. Just looking back at the functions here, the scale argument is the last one. So we have to specify a color followed by the scale. I think I like the white color, so I think we'll keep them white, and then we'll specify a scale of 4. That'll make them way, way larger, but I think it'll be a lot cooler as score numbers. Let's take a look again. And, well, yeah, they're a lot larger, but I don't like how this score number is not quite lined up with this score number. Now, we could go the route of just changing this number until it looks good enough, right? But we can talk a little bit about why this is happening and maybe come up with a more practical approach to lining up these things correctly. As I said before, figuring out where to place things in a game can be very annoying and difficult. Let's look at that 0 text we place on the screen. The reason why it's placed at those positions is because if we had an imaginary grid, and we just happen to say that this line, or this point I should say, was 30, 30, you'll notice I'm highlighting the upper left corner of these zeros, because once again, this is the screen width minus 30. I'm just abbreviating here. Screen height, or not screen height, we decided not to do that. It's just comma 30. Once again, it's using the upper left corner. So in theory, if we wanted to make this even, the actual calculation is to find out what the width of this string is, subtract it this way, so that it's more like, ideally we want it to be right aligned, right? That way it's actually even with the other side of the screen. So our goal is to subtract the text width. Now luckily, the Pixel Game Engine provides us with a utility function for that. I will demonstrate that now for you. If we know what our string is, which is enemy score, we can first store that into a string variable. To specify a string, you have to put std : and then the word string, and this is our type. So yes, you have to type out all of this to use a string type. I'm going to put the enemy score into this string variable. Oops, I should not have named this the same thing. Let's call this enemy text. Ideally, I would call it enemy score text, but it's getting a little wordy now, isn't it? So we're going to store the string version of enemy score inside of the enemy score text variable. And then what we can do, there's this function called get text size. And getTextSize allows us to specify a string, and then it returns a vector containing the size of the text in width and height variables. So getTextSize returns a vector, which means it provides two components, an x and a y. If I type a dot after this, one of the available components is the x component. The other one is the y component, which is the height. We're only interested in the width this time, but just showing you that's how you would get them. Since we know we want to subtract the width of the text, we're actually going to put screen width minus 30 minus the width of the text. No, it's getting a little confusing here. And originally we had this in there, but since we already stored it in a variable, we might as well use the enemy score text here as well. Let's just have a look. It's a little confusing. Well, it still doesn't look right. But we thought for sure that was how we did it. The reason why it doesn't work is actually because of the way this was designed. getTextSize returns how large the text would be if it was scaled with the size of 1. You'll notice here, we're actually scaling the text by 4 times its original size. So in order to get the proper size, we actually have to multiply the width of the size of this text by 4. And now it is actually in the correct spot. And I know that's quite a bit more complicated than just messing with the numbers until you get the right number, but I assure you that this is worth it as like additional polish for your game if you can figure out positions of things like this. Imagine if your score got up to 10 per se. Let's just set the enemy score to like 100 real quick. I'm just going to give the enemy score 100 points. You can see now the number properly adjusted itself because its width is accounted for. So it's actually moved over this way. Whereas before, when we didn't account for the text size, and we just put it 30 pixels from the left strictly, because the origin was on the left, you would only see the number 1, the last digit in the number in the first place. So you can see to do effects like this, you're going to have to learn stuff like this. And maybe you don't understand it completely now, but taking the time to draw it out, look at the formulas, look at what tools you have, say this is what I have to do. These are all going to be things you're going to have to learn if you want to develop games. So this is great. We have scoring, we have collisions, we have input, we have an AI to play against. The only thing we're really missing is like a win condition. And a lose condition, I guess. In order to handle this, I usually do what are called game states. And we can talk about game states real quick. So, game states are used to help control the flow of your game. Right now, we've basically been in a running game mode or playing game mode, right? But let's say we won or we lost. We don't want the game to keep running, right? We want to do something else. We win. That can be one state. We lost. That could be another state. And maybe we might even have a title screen. And the title screen might be where we hit like to play the game, to start the game. All of these can be individual states. At no point will anything while running game matter in the title screen. And when we win, we don't want the game to keep running. We want to stop the game from running. And same with losing. We just want to say, oh, we lost. And how you go between these states can be drawn accordingly. We go from the title screen to running the game. We go from running game to either the win game state or the lose game state. And finally, in both the win and lose states, we go back to the title screen. So we can make a system that incorporates all of these different states. The easiest way to do this is to use what are called enums. Enums are a way for us to represent values or numbers, but as text. In C++, you define an enum by typing the word enum, stands for enum or enumeration, followed by the name of the enum. In this case, I'm going to use this as call it the state. And each state can have its own name. So in our little diagram, we have title screen, that can be 1. All variable names have to have, cannot have spaces. You can have underscores though, so I like to use underscores as spaces. We can have a running game state, we can have a win game state, and we can have a lose game state. And I think this is a good way to separate our game and introduce the concept of states. Now, in order to control our game using these states, we need to actually create a state. Believe it or not, you just created your own custom type of variable. So we specify the type by saying state, followed by the name of it. I'm going to call this the game state. This is like the official state of the game at that moment. And I'm going to set the game state, at least at the start, to be equal to the title screen. You can kind of see how these enums are actually pretty powerful already. We can specify names instead of numbers. And if you look, my IDE actually says, hey, this is the number 0. This is the number 1, the number 2. But it's doing this all internally. This is why enums are pretty cool. Internally, they're just numbers. But we can see them as something more meaningful in our code, so it's easier for us to read. That's why I introduced this pretty early. It's very handy. And we're about to see the power of using game states. So how do we actually utilize the game states here? Well, since we're going to be starting the title screen, we don't want to be displaying all this like ball stuff and moving the ball and everything. All of this code we don't want to run right now because it has nothing to do with the title screen. So we have to segregate it using a giant if statement. Since we know all this stuff has to be while the game state is running game, we're going to actually make an if statement that says if game state is equal to running game, then do all of this, including all that drawing stuff. I'm just going to wrap it all in this giant if statement here. And properly indent it so we can kind of see what's going on. Let's run the game real quick. You'll see we have a completely blank screen, and this is not an accident. This is because we're currently in the title screen. We just haven't done anything in the title screen yet. But, as you might expect, if I were to change the game state to running game, now all of a sudden, well, we're playing our game again. And you can see I forgot to set the enemy score back to 0. I'm letting him cheat right now. So maybe we should do that real quick. Set the enemy score back to 0. And we'll set our game state back to the title screen. So you can already see how we're going to utilize these. by using one variable to control the flow of our game, we can make sure we only draw and do the things that matter and control our game that way. So if game state is equal to title screen, I want to do something else. And then if game state is equal to win game, I want to do something else. And if game state is equal to lose game, well, I also want to display something else. So now we can fill all of these out with different functions in our game. And if we want to just be nitpicky here, you could put else statements here, because if game state is one thing, it's not going to be the other things, right? We already know that. We don't have to check for every single one of these. And I bet you the compiler will optimize this out anyways, but that's a more technical topic, and we're not worried about efficiency right now. So let's talk about the title screen since we're in it. Let's draw the name of the game, and let's make it so it says press space to begin. I think that's a fair thing we can use there, right? So we're going to have it draw two things on screen, and ideally I want them centered. And you already know what I'm going to do, because I like to make sure we're drawing things in the right places. I'm not going to guess where we're going to draw this text. We're going to calculate it. So I'm going to draw Pong in giant capital letters, and I want it to be centered. I want the text to be pretty large, and then in slightly smaller subtext, I want to say press space to begin. And then, of course, if the user presses space, we will move to playing the actual game. That's kind of what I want to go for. And I want these to be centered. I want the text to be centered. So centering text. You might remember my little tidbit about how we centered our paddle. Well, we can do the same thing here. Our origin point is the upper left corner. If we want to center something, we have to figure out what half the width is. That's a little larger than half. Take half the width and half the height and add them to figure out where the center point is. And then once you figure out where the center point is, then you just subtract those values. So you figure out where you want your center point to be, and you subtract half your width and half your height to get a centered text. So in the case of our point in the middle here, the center wants to be screen width divided by 2. Wait, that was right. Comma. Let's say this is like 80 pixels down from the top of the screen. We'll say the center point of the other text should be also in the center, but let's say it's at 240. I think those are decent spots for the positions of our text. Kind of like where this is going. So let's see if we can make that happen. So here we have the title screen. Let's start by drawing our text. So we're going to call draw text. We're going to start by drawing Pong. I'm going to put it at screen width divided by 2, comma, the Y position is 80, and I'm going to draw the words P-O-N-G in giant letters, and I'm going to make the scale be really, really large, like 6. I forgot the color. Let's actually make the color be black. Draw text. I think that should be what I... It's not draw text, is it? How about draw string? That sounds right. Draw text, draw string. Now, in order for this to be centered, like we said, we have to take half of the text size. So, again, we need to get what half the text size is for this. So I'm going to extract this to a variable. To do this, we again type std : string. We're going to call this the title text. I'm going to set it equal to Pong. The next thing we have to do is figure out what that text size is and subtract it from the x position. So we need half of it. So I'm going to do, once again, get text size of the title text dot x, because x is the width of that title text. And I will also point out here that this is on a scale of 1, so we have to multiply by 6. And the actual text will now be title text. That will center it along the horizontal axis. If we want it to be vertically centered along the vertical axis, we can also subtract the height times 6 divided by 2. I forgot to divide by 2, so that was kind of my fault. We only want half the width and half the height. If you were to simplify this mathematically, you would actually end up with times 3, but I'm not going to simplify it right now. Let's have a look. Oh, that's beautiful. That's exactly what I would want. Perfect. Let's do the other text. Very similar concept. I'm going to remove that now because it's probably going to cut off the other one. We'll see. But it's a very similar idea. We'll have the spacebar text. That's what I'll call it. It'll say press space to begin. We'll have another drawString function. Here we'll get the text size of spacebar text and display spacebar text. However, we do have to change the size. Let's make it a bit smaller, like a size of 3 instead of 6, which means we also have to change what we multiply it by. That way it's not going to space it out too much. And we have to lower the y position from 80 to 240. So 240 minus that. That puts us in a really good spot. I really like how that turned out. The next thing we have to do is add some logic while we're at the title screen. We have to say if, again, we're going to get a key. This time we're going to get the OLC key of space. And we're checking if it's pressed this time, not if it's held, and definitely not if it's released. And if it's pressed, we're going to change the game state by setting game state equal to running game. And this will immediately break out this logic, which means all the stuff from here gets removed, and it starts running everything in here. And this is why game states are so powerful. By setting what the game state is, you immediately change what you're doing in the game. So here, I haven't done anything yet. I'm going to press space. And you can see the game has begun. Now we just have to add a win and lose screen. In order to preview the win and lose screen, I'm actually going to set the game state at the start to immediately be at the win game screen. That way we can kind of see it. On the win game screen, I think we're going to make the background be a little fancy. So right here we have clear, very dark gray. I'm actually going to make it so when we're in the win game screen, we're also clearing it to a... let's do like a dark blue. And then we'll make it so we draw some text saying you win. So we're going to make a win text. This is going to be very similar to the title screen, by the way. So I'm not going to quite draw it out on the notes because we are pretty much going to do the exact same thing. So we're going to say you win in giant letters. And we're going to have some subtext just like before. We're actually going to call it spacebar text again and say press space to go back. This is going to be quite wordy, so I think what I'm going to do is put a new line character here to the... Let's not be wordy. Let's just say to play again. Press space to play again. I think that's good. And because I already have two versions of text that I like, I'm probably going to reduce the size of this one to 2 because it's going to be really, really large. Instead of displaying title text, I'm now going to display win text. Also, I'm not going to make them black because we're going to have a dark blue background. I'm going to make them white instead. That looks pretty good. Let's see what the win game screen looks like. Excellent. And if we press space, what we're going to do is return to the title screen. So if space is pressed, set the game state equal to the title screen. We're going to do something very similar for when we lose the game, but instead of dark blue, let's clear the screen to a dark red. We're going to say, you lose. Press space to play again. And I'm going to rename refactor the variable to be lose text. In VS Code, you'd press F2 to do this. In Visual Studio, I don't know the keyboard shortcut, but you would usually do right click and then rename. And that lets you refactor it, which will automatically change all instances of that. Let's set the game state to lose game real quick and have a look at that screen. Okay, so this is what the lose game screen looks like. Excellent. Finally, we need a win/lose condition. And the way to do that is in the running game, we're going to see if either of us score more than... I was going to do 7, but I think 5 points will be good enough. So, if player's score is greater than or equal to 5, it's never really going to be greater than, but just to be safe, right? Then we win. So let's set our game state to win game here. If the enemy score ever ends up being greater than or equal to 5, then we lose the game. Just to speed things up, I'm also going to make the initial ball speed be a little faster. So at the top here, I'm going to start the ball at 100, or maybe not 100, let's say like 60 instead of 50. And I'm also going to make it so our reset code sets the speeds to 60 instead of 50. If I really wanted to, I can make variables to say what the initial ball speeds are. But for now, I'm just going to leave it like this. Oh, and set our game state to be the main menu so we can try playing our game for real. You think I've covered everything, or you think there's still a bug? Spoiler alert, there's still definitely a bug. But we'll play the game a little bit, and we'll see what happens. See if you can figure out what I forgot. But we're pretty much almost done with the game now. We have a full-featured game from start to finish. In the meantime, I'll try to score 5 points. It'll probably take a little bit. I guess the fastest way to complete the game is actually to lose, because the AI will not lose very easily. But I guess we should verify that I can indeed score a point, because we haven't actually verified that, have we? It should work, but you never know. Yeah, it takes about like 7 or 8 hits for the AI to lose. Yeah, so we got a point there. I'm gonna purposely lose now, just for the sake of speeding things up. And then we'll look at the one core thing I forgot. So after this, we should end up at the lose game screen, since we lost. You lose. Excellent. We're done, right? Let's try to play again. You lose. Wait a second, we didn't even play the game. Why are we still losing? The reason why we're still losing is because we didn't actually reset the game when we won or lost. So, ideally, when we start the game, when we switch to running game, let's make sure the game is in a state that's playable, right? So what we should do is reset the ball. Well, let me think. If somebody scores the last point, the ball does get reset. So we don't have to do that. But what we do have to do is reset the player's score to 0 and the enemy score to 0. That way, when we run the game, we don't automatically lose because we already have a losing score. And that should pretty much be it. I'm going to once again adjust the ball speeds to start at, like, let's say 80. Just to once again speed things up a little. And I think we're pretty much good there. If you want to randomize the ball speeds a little bit, you can choose to make them go left or right every once in a while, instead of just always going in the same direction. There's this nice, very crude, but useful for our scenario, random function called rand that we can use in order to do this. So let's just play our game one time, make sure everything works fine. I sped the ball up, so we should be able to clear a little faster now. Let's see if we can win this time. And let's also make sure, of course, that the score's properly reset when we're done playing the game. So this is the first of a couple of videos that I plan to do to teach a bit about how to make games, the core concepts behind making games, and what is required in order to, well, make something. It's quite a bit involved, and games, well, I didn't have any real problems making these things, but that's also because I planned them pretty well. If you plan your games out well and take the time to actually do the math, do your drawings, do your planning, then you too will be able to make it so your games aren't completely ridden with bugs and you won't get stuck. But this takes a lot of time. Just because everything went smoothly for me doesn't mean things are necessarily gonna go smoothly for you, especially if you're like newer to programming. Not knowing how to do things or not really sure of what the algorithms look like is really going to be what hinders your ability to just start making games, essentially. But that's why I'm here to help. I'm trying to make some videos that go through making a game and explaining all the logical concepts and math and design elements we need in order to completely make a game. The Pixel Game Engine is also great for making your prototypes and even real games because you learn all the fundamentals. You're given like a sandbox to play with. It's very easy to get graphics on the screen, as you can see, and you get to focus on the actual game making, which I think is really important. There are these game engines out there that require you to learn a lot of fancier things, and yeah, that can be great when you're more advanced and developed, but when you're starting out, you need something simple that you can play with. Here I'm at the win screen. I'm going to press space, and then press space to begin. As you can see, our game state has all been reset, and we're ready to play again. Very good. And we can keep doing this forever and ever. If we wanted to randomize the ball positions, again, we can use a random function here. And the way this works is rand returns a random number between 1 and some crazy number like rand max, like 32,000 something. But what we want here is a random number between that's either 0 or 1, and then that determines if we flip the ball or not. The way we can apply randomness, let's say we had a number like 37, right? Just some random number, and the next time we had a number 452. These are completely random numbers out of the blue, and your rand function is going to generate these. How do we scale it down to be, well, 0 or 1? We're going to say if the random number is equal to 0, then we're going to make the x ball speed be, we're going to flip the x ball speed. X speed gets multiplied by -1. And if the random number is 1, then we want to set the x speed multiplied by, or excuse me, we don't actually need to worry about the other state. We're just saying if random is 0, we need the x speed to be times equals -1. If it's 1, well, we're not going to do anything. But we do need to choose between 0 or 1. We don't want any of these other fancy numbers here. So how do we scale it? Well, there's a trick we like to use where we get the remainder by dividing a number by 2. You can see I use the percentage sign here. And the percentage sign is what we like to call modulus. Something you can look up later if you're curious. Modulus says take this number, divide it by this number, and the result is going to be the remainder. If you take 37 divided by 2, you end up with 18, remainder 1. Let's look at another case. 452 modulus 2 equals 0. If you take 452 divided by 2, you end up with 226, remainder 0. Interesting, right? You can start to see how this would give us a random number between 0 and 1. if rand returns 37,000, we can modulus that by 2 to get the number 0, and so on and so forth. It also works as an even-odd checker. Just a little trick you can use in the future if you need something in that regard. So we can actually implement that. We can say, we're going to follow our logic here. We need to store a random number. So let's just say random number equals rand. Just like that. And then we're going to say modulus 2. We're actually going to modulus 2 it here. And then it'll be a number from that's 0 or 1. Get a random number that is 0 or 1. If random number is equal to 0, then we said we want to flip the ball x speed by multiplying it by -1. And that's fine. That gives us a random chance that it will be flipped, a 50% chance. We also want to do it again for the y speed, but let's make it another event. That way it's a little more random. So we'll get another random number. Now we don't have to say int random number again because we already defined what its type is here. We're just going to reassign it, set it to another value. If random number is equal to 0 again, this time set the ball speed, multiply by -1. And we can do the same thing down here for enemy scoring. Let's test it out. Press space to begin. Let's let the enemy score. You can see it went down and right. That's how it normally goes. Let's let the enemy score on us again. It went down and right again. Let's let the enemy score on us, or let's let us give a score to the enemy one more time. It's down and right. I think something's not working. Aha. So it looks like we put the ball x speed, or we set the ball x speed before after multiplying it. So no matter what we did to the number, we just set it back to 80 anyways. Oops. These kinds of bugs or mistakes happen all the time. You can see it went to the upper right this time. I'm going to let the enemy score on me one more time. Now it goes down right. And one more. This time it went down right again. So as you can see, it is quite random. Random enough to where we get different results every time we play. It's not perfect, and it is very crude, but it's enough for now. One other thing I'll mention is that you usually have to seed your random numbers. So up here in onUserCreate, we usually use what's called srand, where we assigned a seed. And you usually use this time method so that it takes the time of your system, and that's used to seed the random number generator. I'm telling you these terms in case you want to do some research on what that's all about. But this just makes it so it's actually randomized, and you won't always have the same random numbers every single time you play. We can also randomize the ball x and y speeds a bit if we really wanted to. That might be an exercise left to the reader. But with that, we do have a fully functioning game. So hopefully you guys like that. I will also leave the entire source code on one of my Git repositories for folks to take a look at and play with if they want to. I'll leave that in the video description as well. But that's pretty much all I wanted to demonstrate today, and we went through a lot. So yeah, awesome stuff.